This is slide number 44 and I am your presenter Asloob Mudassar. Today we are going to discuss one application of the Fresnel diffraction formula, but two applications will be described. For example, the two cases will be presented. One case is the Fresnel diffraction by a square aperture, and the second case is Fresnel diffraction by a sinusoidal amplitude grating. So in slide number 44, we are only going to discuss Fresnel diffraction by a square aperture. So you see that a square aperture in the figure has been shown. The square aperture is lying on the zeta eta plane. The width of the square aperture is 2w on each side, from minus w to plus w, and you know that there is a clear aperture of this width, and around that there is an opaque region through which light cannot pass. And the field at this plane, that is at the eta zeta plane within the clear aperture, is known. We want to calculate the field contribution at the point P naught on a plane which is the xy plane, and this plane is also parallel to the zeta eta plane and separated by a distance capital Z from that one. The z axis passes through the origin of both coordinate systems. So let's describe them as we have given in the statements. A thin sinusoidal, a thin square aperture of a width size 2w centered at the origin of the zeta eta plane is illuminated by a normally incident plane wave of unit amplitude. So notice that we are using a normally incident plane wave of unit amplitude. Field just before the aperture is equal to 1. That's why we have written 1 due to unit amplitude. And we have ignored the constant phase of the wave because the plane is normally incident. The phase on the whole plane is constant. We can ignore the constant phase. Field just after the aperture is, because the field has to pass through the square aperture, and now the field becomes, after passing through the square aperture, the field becomes equal to u of zeta eta is represented by two rect function. One rect is zeta over 2w, the other rect is eta over 2w. So both rect functions will define the square aperture. So you know that this field, that is u of zeta and eta due to the normally incident plane wave, is known as given in equation number 34. We want to determine the Fresnel field at a point P naught at the coordinate x, y on the xy plane, which is parallel to the zeta eta plane and located in the Fresnel region at a distance capital Z from the zeta eta plane. The geometry of the problem is shown. The Fresnel formula of equation 9 is appropriate for this problem, and this is listed below. So the field at the point xy, which we have written u of xy, is equal to e to the power iota k z over iota lambda z, and the double integration from minus infinity to plus infinity. The known field is u of zeta eta, and the others are the parameters of the integral. So substituting and replacing u of zeta eta with the two rect functions in the second step, so rect of zeta over 2w and rect of eta over 2w, and the rest are the parameters of the integral, that is of the Fresnel integral, as given in equation number 35. Now we can omit these two rect functions, and at the same time, if we omit them, we have to replace the limits of the integration. So for example, the limit of the integral can be adjusted by omitting two rect functions. So we have adjusted the limit. Both integrals goes from minus w to plus w. And you know that there are no more rect functions because the rect functions outside this limit is 0, but within this limit, that is from minus w to plus w, on both integrals the rect functions are 1. So that's why we have replaced the rect functions by 1, and at the same time we have replaced the limits from minus w to plus w as given in equation number 36. The integral is separable in zeta eta coordinates as given. So we have the dependence on the integral on the two variables x minus zeta square plus y minus eta square. So the two integrals can be separable, and which is given in equation number 37. So we have the constant phase vector, then we have I of x in the second row of equation 37 and I of y. because I of x is represents the integral, which is 1 over lambda z, square root of lambda z, and the integration from minus w to plus w, and e to the power iota k over 2z, and in the exponent we have x minus zeta whole square with respect to d zeta. The similar is the second integral, but only x is as x has been replaced by y. The both integrals are very similar. So if we evaluate one of the integrals, the other integrals can be written directly by just a change of variables. So the integral represented by I of x, I of y are identical. We shall solve one of them, which is given in equation number 38, I of x in equation number 38. So you see that we have just written the exponent in another form as given in equation number 38. Now you know that actually we want to simplify this integral given in equation number 33 using some limits. So we can replace the limit within that is 2 over square root of 2 over lambda z multiplied by x minus zeta will be replaced by tau, and if you take the derivative then d zeta on the left hand side will give you minus square root of lambda z over 2 and multiplied by d tau. So when zeta is equal to minus w, tau will be equal to this, equal to 2 over lambda z square root of this one, and then x plus w multiplied to it. And if zeta goes to plus w, then you know that tau will take the value of the square root of 2 over lambda z multiplied by x minus w outside the square root. So the equation 39, in the equation 39, we have introduced some variables. These variables will be plugged in equation number 38, and then we have the simplified version, because we are making these substitutions because we want to write the integral in some suitable form that are historically known to us. So the integral is transformed as given. I of x is equal to 1 over square root of 2, and the integral limits you know that are shown, which we have calculated before. And the exponent is now e to the power iota pi by 2 tau square, and the integration is with respect to d tau. So you know that now we have arranged the limits in a different way, that is we have x over lambda z in both limits, x over square root of lambda z minus w over lambda z square root, and the upper limit is have a plus sign, the lower limit has a minus sign. So this is equation number 40. Now you know that we are going to making another changes in the limit, we are introducing another parameters, for example the scaled variables, so that we can further simplify the limits as given in equation number 41. So the introducing scaled variables, so x over square root of lambda z will be represented by capital X, and w square over lambda z will be represented by nf. Nf is known as the Fresnel number, very important number. So here, since we have w over square root of lambda z in the limits, so we shall replace those quantities, that is w over lambda z square root of that one by the nf square root. So now in 41, so now the integral in equation number 40 has been replaced by as given in equation number 42. So the limits you can see that has been changed from So we have capital X and square root of nf as the limits. And you know that these are the two limits, one from x minus square root of nf to x plus square root of nf. And we want to represent the lower limits, we want to break up this integral into two limits, both going from 0 to the upper limit. So the lower limit we want to be 0. So you know that we have set up this one as in equation number 42. Now by definition of the Fresnel integrals, because here we have written equation number 42 in such a form that we can introduce the Fresnel integrals, which are given in equation number 43. So Fresnel C of alpha is equal to from 0 to alpha cos of pi over 2 t square with respect to integration with respect to dt. And similarly Fresnel S of alpha is equal to the limit from 0 to alpha and sine of pi over 2 t square, integration is with respect to dt. So you can notice that the upper limit in both integrals is alpha. And we have Fresnel C and Fresnel S as a function of alpha. Now you know that we can represent the solution in terms of these integrals. So the solution of the integral in equation number 42 is given below. So I of capital X, that is the solution in one dimension, in variables capital X is equal to this one. So you can read this one, that we have a square root of 1 over 2 on the left of each curly bracket, and you know that we have Fresnel C as a function of square root of 2, and within the bracket we have x plus square root of nf plus iota times the Fresnel S, and within the argument of that we have square root of 2 multiplied by within the parenthesis x plus square root of nf. So the same is written for the lower, but you know that the sign could be different. For example, in the upper row we have the sign x plus, and in the lower we have the sign x minus. So this is the solution of that one in terms of the Fresnel integrals as given in equation number 44. Now you know that we have written this one, but now we can collect the Fresnel C terms and the Fresnel S terms. So in equation number 5 we have collected the Fresnel C terms in the first row and Fresnel S terms in the second row. Now you know that we have to calculate the intensity, which is similarly we can write the solution for the y variables, for the y integrals. So we have written I of y similar to that one. Just the difference between equation number 45 and 46 is that we have replaced the capital X variables by the capital Y variables as indicated in equation number 46. Now we can very easily write the amplitude Fresnel field or the Fresnel amplitude in 2 dimension using equation number 37, which is listed in equation number 47. So we have multiplied by the two terms, that is equation number 45 and equation number 46 have been multiplied, and we have written them. So the first term, the first curly bracket represents the equation 45, and the second curly bracket in the second row represents equation number 46, and the total becomes equation number 47. So you see that this is the amplitude. But you know that sometimes we are interested in the intensity, because intensity is the quantity we can visualize practically. So let's calculate the intensity. So I of x comma y in variables capital X and capital Y is equal to u of capital X comma capital Y multiplied by the complex conjugate of u as a function of capital X and capital Y. So multiplying, so taking the complex conjugate of the equation number 47 and the equation 47 itself, plugging that one and simplifying this one, we are getting the result as given in equation number 48. So you can see that I of x comma y is equal to 1 over 4 times the two curly brackets. One curly bracket contains, you know, that terms which are x plus square root of nf, that is the cos terms, and then the second and then the Fresnel S terms, and similarly in the second curly bracket we have the first terms depending upon the y in the Fresnel C integrals involving the y terms, and then you know that the Fresnel S terms in the fourth row involving the y variables. So we can immediately write down and we can immediately understand these terms by the multiplication of the equation number 45 and 47, because we have written them as such. Now you know that in order it is difficult to visualize the two-dimensional plot. So what we do is that we can take only the one-dimensional plot. We can extract the one-dimensional intensity from equation 48, so that we can realize the plot of those intensities. But you know that here we can replace x, capital X, in terms of the small x quantity which we have given earlier. For example, over here in equation number 41, so we can replace capital X backward in terms of x over square root of lambda f, and we shall keep the nf there because nf is a very important number. So we can write down those intensities in terms of real variables x. So 48, equation number 48, we have taken only the x part of that one, and we have plugged in the backward variables, that is capital X replaced in terms of small x divided by the square root of lambda f. So you see that these two terms are very well explained in the curly brackets. Now we can plot this I of x. The Fresnel number f, you know that as such is present in equation number 49. The Fresnel number nf that we have defined in equation number 41 has a highest value close to the aperture. which decreases as we move away from the aperture, and NF helps to identify the Fresnel region. So the Fresnel number helps us to identify the Fresnel region, because the numerical value of the FL will decide that whether we are in the Fresnel region or we have gone in the Fraunhofer region. So the discussion below will make it clear. So Fresnel number for 3 different aperture widths has been plotted versus versus distance from the square aperture. So look at this one, the figure. We on the horizontal axis we have the plot of capital Z values going from 0 and in intervals of 20, 40, 60, 80 and 100. So these values are in millimeters, and you know that we have plotted the NF, that is the Fresnel number, on the vertical sides, and we have that labeled the axis by 100, 200, 300 and 400. So you see that we have used 3 values of the width of the aperture in one dimension. The lowest value is 2W is equal to 0.8 millimeter. The next higher value is 2W is equal to 1.6 millimeter, and the third value is 2W is equal to 2.4 millimeter. So you can see that for the greater value of the width of the aperture, we have the larger value of the NF. We start with the larger value of the NF. So you know that as Z increases on the left hand side, all the values, that is the Fresnel numbers, will decrease. So you know that you can notice the decrease of the Fresnel numbers. The Fresnel numbers will decrease immediately for the numbers which is less in width, that is 2W is equal to 0.8. The Fresnel number will decrease very quickly when we increase the Z value. And you know that at the value of approximately 40 or around that, it becomes nearly equal to 0. And similarly for the others. But you can see that with the 2W is equal to 2.4 millimeter, the Fresnel number even is not 0, even we have Z is equal to 100 millimeter. So it means that this indicates that the value is significant at the value of Z is equal to 100 millimeter for the NF number. So it means that we are still in the Fresnel region. Further explanation will also be given where we can clearly mention that for what value of the NF number we are in the Fresnel region. For large distances, so what we have learned from this figure is that for large distances from the diffracting aperture, the Fresnel number becomes smaller and smaller, and when its value approaches less than 0.05, so you see that we have given the numerical value, although it is difficult to show this value on the plot. So when its value approaches less than 0.05, we assume that we have entered into the Fraunhofer region. The diffracted field becomes smooth in this region. So what will happen? The diffraction field, the smoothness will appear in the diffraction field when our Fresnel number is less than 0.05. And below this number we are in the when the number is greater than this one, it means that we are in the Fresnel region or in the near field, because the two terms are used, the near field or the Fresnel or the Fresnel field or the Fresnel region. So these numbers are so these names means the same thing. And similarly Fraunhofer region or the far field region, Fraunhofer region or the far field region, both means that we are beyond the near field or we are beyond the Fresnel region. So let's further talk about this. Plots of Fresnel number versus the distance from square aperture. This is what we have shown earlier. You know that this one, in this plot we have shown the plots of a Fresnel number versus the distance from the square aperture. Now we show more different plots. As we move away from the diffracting aperture, the diffracted field becomes broader in size and smoother in variation. The Fresnel region is extended with the larger aperture sizes. Thus the smaller sized aperture, the Fresnel or the near field diffraction region is shorter. So actually these are the plots of the Fresnel intensity in one dimension. That is, we are plotting I of x. In these plots So plot of a Fresnel intensity in 1D, that is the plot of I of x at different distances due to the square aperture of width equal to 1 millimeter and lambda is equal to 632.8 into 10 to the power minus 6 millimeter. That is, we are using the red wavelength of the helium neon laser, which is operating at this wavelength, and we are assuming that our width is constant in all these plots, and the width of the plots and the width of our square aperture is 1 millimeter. So what we are going to change? We are going to change actually the distance of the from that quantities, that is I of x. We are going to plot I of x. So it means that we are plotting x on the horizontal axis and I of x on the vertical axis. So look at these plots. So you see that in the first plot where we have z is equal to 100 millimeter and the NF value is 39.5 millimeter. So it means that from the z is equal to 100 millimeter is that we are very close to the aperture. So look at these variations in the intensity. Very rapid fluctuations in the intensity can be noticed. And you know that the region of the intensity is nearly equal to the region of the width of the aperture, which is 1 millimeter, that is going from minus 0.5 millimeter to plus 0.5 millimeter, because we are very close. So when we move away, that is when we move further away, that is when we are going up to minus 1 to plus 1 on the x, in the x-axis, then you know that capital Z becomes equal to 6. Here we are taking capital Z. So you see that capital Z represents the distance from the aperture. So capital Z is equal to 60 millimeter and NF, which is the Fresnel number, is 6.58. And this x, the small x that we are plotting along the horizontal axis, this is not the this is not the distance which is away, we are taking from the aperture, but this is the plot of the intensity, and x is the parameter of the plot of the intensity. So capital Z is the distance from the aperture. So look at this one. You know that now comparing with the previous one, you can see that the signal is better in smoothness as compared with the first signal, which was taken at z is equal to 10 millimeter. So the smoothness is coming into the Fresnel field, but at the same time you will notice that the Fresnel formula has expanded, and now you see that it is going from minus 1 to plus 1 as we plot the intensity. Now in the third one, we have taken z is equal to 100 millimeter, and for that one, if you put z is equal to 100 millimeter and you put the value of aperture width w is equal to 1 millimeter, which we have taken, you will find that the NF value is equal to 3.95. And you can see that our width over Fresnel field has broadened from beyond minus 1 to plus 1, and you know that the variations in the intensity has a little bit more smoothness, because we are getting less variations in the intensity. Now if we go further beyond 1, that is z is equal to 130 millimeter, and if you put the value of this distance and the aperture, which is w is equal to 1 millimeter, you will find NF is equal to 3.04. This is the NF number. So you see that, and the x has gone, the intensity will vanish, and the intensity plot goes from minus 2 to plus 2, and you can see that there is only 3 peaks in the intensity, or 2 on the sides and 1 in the center. So a further smoothness has appeared in that one. So if you go further on the right, we have z is equal to 190 millimeter, NF is equal to 2.08. And you know that the intensity has gone from beyond minus 2 to plus 2, because the intensity has gone to 0. And you know that the sharpness has improved a little bit, because the intensity which was peaking in the center is now going in the inverted shape. And when we go further, that is when capital Z is equal to 290 millimeter, the NF at that value becomes equal to 1.362. And you know that x goes, we have plotted x which goes from minus 2 to plus 2 and beyond that, because the values are so small that we can show them on the plot. And you see that there is further smoothness in comparison with the previous one. That is, we have 2 peaks on the sides and we have still smoothness and in the center. So you see that the smoothness is improving as we go with the further value of capital Z. and the smoothness is appearing in the intensity of the signal, that is the intensity of the Fresnel field. Let's go further. So you see that we are keeping the same parameters, that is W is equal to 1 millimeter and lambda is equal to the wavelength of red wavelength of the helium neon, which is 632.8 into 10 to the power minus 6 millimeter. We are using the same variables. But you know that at that time the same plot are given as we have given over here. The only difference is that we are increasing the value of Z further. So if you increase the value of Z further, that is if Z is equal to 350 millimeter and F value is equal to 1.129, and you know that we have plotted the intensity over here. So you can see the smoothness by yourself. So here in the second one, in the middle, we have Z is equal to 450 millimeter and F is equal to 0.878. The number is, you know, that now less than 1, and you can reduce and you can see the intensity is further going to be smoothened. And even for Z is equal to 590 millimeter and Z is equal to 1100 millimeter, then we have gone up to Z is equal to 3100 millimeter, where you can notice that NF is equal to 0.127, much less than, you know, that 0.1 of the order of a 0.1, and you see that the intensity is highly smooth over here. Besides that, we have some side lobes which have diminished values and only a single main lobe over there. So when you have Z is equal to 7100 millimeter and F is equal to 0.056, so very close to, you know, that 0.05, where we have mentioned that when we are less than this number which we have shown in the last for the last figure, which is 0.056, if we are less than this number, we are surely in the Fraunhofer domain or in the far field domain. So this is the last limit for the Fresnel domain to hold. You can see that we are approximately entering now in the region of Fraunhofer field. So you see that you can notice that the smoothness. So you see that, and you can notice also the width of this intensity, which is going from -10 to +10. And at the same time you can notice that the height is just 0.2, that is the height has decreased. So from all these plots we notice that the width of these signals are going to be increased, and at the same time the height of the peaks are going to decrease, because the total area under these curve has to be constant. So the smoothness will improve as we move away from the aperture, diffracting aperture, as indicated in these one. So these are the findings that we have obtained from the analysis of the above plots. Now we are summarizing those findings. Number A, when we are close to the aperture, for example Z is equal to 100 millimeter, where NF value is 39.5, the field behind the aperture is the geometrical shadow of the aperture with rapid variation in intensity across the aperture, which we have shown over here, this one. Now in part B, at larger distances from the aperture, the variation in intensity becomes smoother. We have seen that the smoothness is gradually appearing as we increase the value of capital Z, that is as we move away from the diffracting aperture. The point C is that the diffracted field becomes broader with the distance from the aperture. We have seen that when we go away from the aperture, the overfield broadens as well as smoothens. At D, at a very large distance, for example Z is greater than or equal to 7100 millimeter, or equivalently at a very small Fresnel number, NF is equal to less than or equal to 0.05, the diffracted field is expanded by more than 20 times the size of the aperture. So you see that over aperture was 1 millimeter in size, and here you can see that the width of the last plot is from -10 millimeter to +10, that is the 20 times the width of the aperture. So the diffracted field is expanded by more than 20 times the size of the aperture, where the diffracted field becomes very smooth, resulting in a single main lobe and a few diminished secondary side lobe peaks, and the field is regarded as a Fraunhofer field. And the E is that the area under each diffracted pattern remains the same. So this is the end of slide number 44.